And happy Tuesday evening. Hi, I'm Gary, ham radio call sign Whiskey 4 Echo Echo Yankee, and this is a general class amateur radio course. We have been working through the American Radio Relay League License Manual for General Class. That's this one, the 10th edition. It's a new book this year, July 1st. Is when it came out, and it has the latest question pool, which will be valid for about 3 years. So this is the book that we're using to study from, and we go chapter by chapter each week and try to cover the test questions. This is not an electronics class. This is not a comprehensive class. We can't go into depth, but what we do is we focus on amateur radio licensing, the test questions, the answers, with the goal to have you pass your general class upgrade test sometime in November. Of course, you don't have to wait until then, because one of our students on the YouTube side, who has been watching our classes on YouTube, Chris Marchi, went and took his test on Saturday at the test session in Greenville, South Carolina, where Dave Ivey was actually one of the volunteer examiners. And so I have asked Chris to join us in our Zoom classroom tonight. And Chris, would you mind introducing yourself and then tell us a little bit about your experience, please?
Yes, my name's Chris Marquis. The actual testing part was almost the easy part, to be quite honest. The studying part was kind of more challenging to me. And I did skip ahead a little bit and looked at your older videos on the chapters we haven't done yet. So I kind of went ahead and did that. And once I got all the chapters watched and what notes I took, I just started taking the practice tests. And I kind of figured if I could get around the 90 percentile, 90, 91, something along those lines, I was probably ready for the test. But going down there, it was easy. I mean, everybody kind of got through the paperwork and told me what I needed to do, gave me the test, and then talked with me afterwards. And as far as just answering some attendant questions and some other type stuff that I had to take care of.
Well, Chris, did you feel that the volunteer examiners, everyone there, they were on your side? They were trying to help you?
Oh yeah, it was no problem there. They were all nice guys. So, like I said, the testing part was really the easier parts of it.
All right, I'm going to ask you a hard question. Were there things about the class that we should change that would have made it easier for you?
No, I don't think so. And I've watched or tried to watch several different groups that do similar type videos, but yours are probably the better one, to be quite honest. And I say that because you look at that chapter in the book and then you break it down, and that kind of helped me a good bit as far as studying for it. And I'm a big flashcard guy too, so when I took the tests, practice tests, I just wrote a flashcard on every one that I got wrong, and then I just would study the ones I got wrong constantly, and that's when my percentile started going up on the practice tests.
And practice tests were very important for you.
Oh yeah. That kind of got me to the point where I felt comfortable going down there and actually taking the test.
Wonderful. Chris, any final thoughts?
No, I mean, I had plenty of time to sit down there and do it. I'm not a big math guy or equation guy, but once I kind of remembered the formulas and everything, and that's a very small part of the test too. So I was a little worried about that, but I got through those parts okay. And a good portion of it is just regulation, safety. You get questions from all those different chapters.
Well, wonderful. We're so proud of you, and we do have an extra class that'll be starting out in January. So if you would like to participate in that, we'd be happy to have you along.
I plan on it.
Super duper. All right. Thank you, Chris, for sharing tonight. Truly appreciate it. And so now we're going to begin here talking a little bit about Chapter 7. But before, I've got a few housekeeping chores. So Bruce, if you'd put up the laptop, please. There we go. So this was our original schedule that we sent out to you earlier tonight. For example, let me turn on my laser pointer. So tonight, antennas, Chapter 7. And in the previous question pool, we had incorporated Chapters 8 and 9 together. That was a stretch even with the old question pool. And now looking at the new question pool, Dave and I consulted, and we decided that for your sake and for ours, that this is the new schedule that we would like to propose. We'll do antennas tonight. We'll do just Chapter 8, propagation, next week. Following week, we'll do electrical and RF safety plus a practice test. And then our very last class will now be November the 14th, where we will take practice tests together. Now, of course, the practice test sessions are optional. You may be already doing practice tests on your phone or with the ARRL site. But this is our pattern, so I just wanted to let you know about this change, and hopefully it meets with your approval, because that's how we're going to do it. All righty, let's go ahead and continue on with the presentation. Chapter 7, antennas. This is a fun presentation for me to do, and it's a fun topic as well. So we're going to start with section 7.0. You don't have a 7.0 in your book because I made it up. But these are some thoughts and concepts and principles that I kind of wish I knew early on in my ham radio career that would have made my understanding of antennas easier. And so we're going to start out, hang on, next please, there we go, with the subject of skin effect. So at DC or very low alternating current frequencies like power lines, 60 hertz, this is a cross section of a wire. Let's say it's a copper wire. Electrons, current, are going to flow through the entirety of the wire. So the entire wire material is being used. An interesting phenomenon, though, as you go up higher in frequency into the kilohertz range, there actually starts to form a gap in the middle of the wire where no radio frequency current flows. And so radio frequency current is in the outer ring of the wire. And when you get up even higher, a megahertz or so, and you start going up, then you get into something called skin effect, where radio frequency current really only travels on the outer surface of the wire. And there's no electron flow, RF current flow in the middle. So this is skin effect. And I asked this question in my technician class, and I'm going to ask it here for you. How many conductors in this coaxial cable are there at radio frequencies? And yes, it is a trick question. But if you'd like, unmute and see if you can ponder an answer.
3.
There are 3. 3, I only see the center conductor and the shield. But the 3 comes from the outer part of the inner conductor because of skin effect, the inner part of the shield because of skin effect, and the outer part of the shield. That explains why when you hook a coaxial cable up to a dipole antenna, sometimes it works and sometimes it doesn't, because we don't ever think about the third conductor, the outer part of the shield. So that's a concept I'd like you to keep in mind. We introduced the topic of isotropic radiators in the technician class. This is a point source antenna with a totally omnidirectional pattern. It goes out in a sphere and all energy goes out in all directions. Well, this antenna is a theoretical construct. It cannot be built, even out in space, because of reflections. But it's something that engineers use as a basis for certain calculations. What we are more likely to be using is a dipole antenna, a half-wave dipole antenna. I'm going to mute you out there. Whoops. Dave, if you'd help me out there and mute folks. A half-wave dipole antenna is cut so that there's a quarter of a wavelength on one side and a quarter of a wavelength on the other side. And the total distance is a half of a wavelength at the frequency that the antenna is being designed for. Well, Gary, how do I know that? Well, this is the classic formula, 468 divided by the frequency in megahertz. It will give you the length in feet. I muted all, so we should be okay. So this is the formula to remember if you want to calculate the distance of your antenna, how big a half-wave dipole antenna is, 468 divided by the frequency in megahertz. Now, I sent you a link to a video that I think is exceptional. It's part of the Ham Radio Now series. And the presentation was called Standing Up for Standing Waves. And if you got a chance to watch it, great. If you have not, it's about 90 minutes long, but it's well worth your time to take a look at. And I want to bring from that video two concepts to consider. A quarter wavelength of wire or transmission line is what they call an impedance inverter. If you have a low impedance at one side, a quarter of a wavelength away, you'll have a high impedance. That's what we mean by an inverter. So if it's a ground potential at one side, it's going to be practically open at the other side if it's a quarter wavelength long. Ground wire, transmission line, coaxial cable, etc. That's the kind of difference you'll see. A half wavelength length of wire is an impedance repeater. So for a half wavelength long stretch of wire, if it's grounded at one end, it'll seem grounded at the other. That's at one frequency. That's at the frequency that it happens to be a half wavelength. Keep that concept in mind. And then there's the concept of impedance. And we talked about, Ohm's law, E over I, R, and here's another pictorial of the volt being the pressure pushing the current through the wire in this case, and resistance trying to resist it. And the same thing holds true with AC current, including the radio frequency currents that will show up on a dipole antenna. We're going to talk a little bit here at greater length. So here is a dipole antenna, and what we see graphed is the current distribution of the antenna. So the center where it's being fed here is the highest current point, and the ends are the lowest current points. They're actually, though, the highest voltage points. Let me show you this. This is a little easier to see. This is a graphic representation of a dipole antenna, and the blue is the current going up and down as the radio wave is alternating cycles, and the voltage at the far ends is going up and down. The center of this antenna is the high current, low voltage point. The ends of the antenna is the high voltage, low current point. And if you plug that concept, those numbers into Ohm's law for AC circuits, this is a construct, but what it says is that the center of a dipole antenna is the low impedance point, and the ends of a dipole antenna are the high impedance points. And for a resonant antenna, that's one in which the reactances cancel. The inductive reactance and the capacitive reactance are the same and they cancel out. What you are left with for a dipole antenna is an antenna with what I call good R, the radiation resistance, that's what we want, and bad R, which are losses, which for some antennas could be bad connections, resistive losses, rusting or corrosion. Could be, for vertical antennas, ground losses. Those are bad R. So what we try to do is to maximize the good R, because that's radiation resistance. That's a resistance that the energy that goes there is actually radiated out into space. Bad R is just lost as heat. That doesn't help us at all. So as I mentioned, the center-fed dipole, the lowest impedance point is at the center. And we say that the impedance of a half-wave dipole antenna is nominally 73 ohms, which is a fairly good match to 50 ohm coax. And if we were here with this dipole antenna, and if I arbitrarily, I just picked an easy number, said I'm going to have an RF current of 1 amp, well, what would the voltage be? Well, voltage equals I times R, so 1 times 73, that would be about 73 volts here at the center of the antenna. And knowing that, and knowing that we had a current, we can say that this also represents a power level of about 73 watts. So for a 100-watt transceiver, that's a nominal voltage and current that you would see in a common center-fed dipole antenna. Well, you don't have to feed a half-wave dipole antenna at the center. You could actually feed them at the ends. Then we could say it's a voltage-fed antenna. The impedance at the end is very high. The voltage at that point could be hundreds of volts, and so what you do is you use a transformer to transform the 50 ohm coaxial cable up to a higher impedance that might more closely match the end of the antenna. So 9-to-1 is a common balun used for end-fed dipole antennas. But you're not limited to that. I've seen 49-to-1 balance being used for end-fed. Just know that if you're doing this, you're feeding at the highest voltage point at the end. The current is going to be practically nothing, so you don't need very strong, large conductors at that point. Power theoretically will be the same. You're feeding 73 watts if we have an amp of current. But likely the coax feed line will radiate too, unless the balun has a connection for a counterpoise. So the outside of the coax will become part of your antenna. So that's an end-fed. So you may look in the magazines and see center-fed dipoles, end-fed dipoles, and then my favorite, the off-center fed dipole. So we mentioned that we have 73 ohm feed point impedance here at the center. If we move the feed point away from the center so that it's 1/3 and 2/3, you can put a 4-to-1 or a 6-to-1 balun at this point, feed 50 ohms and transform it up, and the voltage and current distribution of the dipole, you can see we're kind of at an interesting point here where they kind of cross, and what happens here is that you can get a good match to the dipole antenna, and the off-center fed feed point impedance is similar, not identical, but similar over multiple bands. So that if we have our 50 ohm radio, we feed it through a 4-to-1 balun and then feed the antenna here, the voltage is not going to be as high as an end-fed, but it's going to be higher than it was at the center. The current will be less than it was at the center. It's about 200 ohms, 200 to 400 depending. Power should be the same, and you are given multi-band operation. Here is a standing wave ratio chart for an off-center fed dipole, a 40-meter off-center fed dipole. And you can see the first SWR dip here for 40 meters, Then there's another one here for 20 meters, another one here for 15 meters, and another one here for 28 megahertz, so 10 meters. So 10 meters, 15 meters, 20 meters, 40 meters, all off of one antenna. Now, the drawback is that there's no harmonic rejection, because this is if you have a second harmonic, say you're on 40 meters on 7 megahertz, and you've got a second harmonic on 14 megahertz, your transmitter's misbehaving, it'll radiate just fine. So that's one problem with multiband antennas. So a dipole antenna, whether it be an off-center fed or end-fed or center-fed, is going to have a radiation pattern kind of like this with a donut. Now this is in free space. On Earth, you're going to be a finite distance above ground, and so this donut was going to kind of flatten out. But we say that the pattern of a dipole antenna is broadside or at right angles to the antenna. So here's the antenna, and here's the pattern, broadside or at right angles to the antenna. And if you kind of want to see it dynamically, in this case, the antenna is up and down, and you can see the radiation pattern off of the antenna and going out to the left and to the right. Now, I mentioned that we're close to ground. We're not out in free space. The closer you get to ground, the more the pattern will start elevating up like this, and the pattern of the antenna becomes omnidirectional. Whereas if this is at an eighth of a wave high above the ground, whereas if you can go a half wave above, then it starts flattening out and you start getting directional lobes off the side of the antenna. So antenna height definitely affects the directionality of a dipole antenna. Inverted V antennas are very popular. They can be off-center fed or center fed. These are largely omnidirectional antennas. So this is kind of the pattern from that. All right, remember, this is all my extra information. There are no test questions we're going over here. Here's one, though, that I'd like you to keep in mind, which I kind of consider the most important thing, a thing that's fooled me a lot of times. And that's this slide. And this has to do with the radiation resistance of the antenna is here on the left, and the height in wavelengths above ground. So here's one wavelength above ground, here's a half a wavelength above ground, and notice that close to the ground, the radiation resistance starts out very low and goes up and up and up. There's 73 ohms. It keeps going up to about 100, and then comes back down, comes back up as you go higher, and it goes back down as you go higher. Note it's regressing to a mean. So that's why we say that a dipole has 73 ohm impedance. But if your antenna is less than a half of a wavelength above the ground, you may get a center point impedance that's 73 ohms or up as high as 100 ohms. Or not. And so, you know, people say, well, how big should I build my antenna? Oh yeah, 468 divided by the frequency in megahertz. But sometimes raising or lowering the antenna can have a bigger effect on matching your antenna to your feed line than even changing the length of the antenna. Now, this diagram is over perfect Earth. Well, we don't have perfect Earth. This is what it looks like over imperfect Earth. It's very similar, except it never really goes as low as the 10 ohms that we saw on the other. It only goes down here like 45, and then starts going crazy high. But the concept is the same. So we looked at that isotropic radiator, that theoretical construct, and we looked at our dipole antenna. And just know that if you are measuring the gain of a dipole antenna versus an isotropic, a dipole antenna has 2.15 dB more gain than an isotropic antenna. Some manufacturers, if you look at the fine print, they'll say this antenna has 6 dB of gain, dBi, over the theoretical antenna, not over the practical dipole. DBD would be over the practical dipole. So know about that when you're reading specifications. So here's our whiz-bang antenna that is rated with a gain of 8.15 dBi. Well, how much is that compared to a standard dipole? It's 2.15 dB less, or 6 dB. So just truth in advertising. All right, here's some questions for section 7.0. There are no questions. All right, but hopefully that gives you a good basis for some concepts, and maybe I've already blown your mind on certain things. But let's talk about section 7.1, dipoles and ground planes. So a dipole antenna we looked at, it was, half wavelength on one, or quarter wavelength on one side, quarter wavelength on the other. A quarter wavelength vertical antenna can be thought of as being a dipole, one section going up, and the other section is mirrored in the ground. And radials can be laid on the ground or below the ground, and it becomes like a mirror surface for a quarter wave vertical antenna. Now, if it's for VHF or UHF, you can actually make radials that are a quarter wavelength long, and so that makes this an antenna that you could elevate and put up on top of a mast. But for ground-mounted verticals, and here's a multi-band ground-mounted vertical, quarter wavelength on 20, quarter wavelength on 15, quarter wavelength on 10 meters, and you have radials that you take out around the antenna. About 30 is the magic number. Radials are just wires that are on the surface or buried a few inches under the earth, and they're connected to a grounding point on the antenna. If you're aware of one of the YouTube channels, DX Commander, Callum, this is one of his products that he sells. His antennas are quarter wave, multi-band vertical antennas requiring a ground plane, looking very much like this. Now, I mentioned there's good R, the radiation resistance, that's what takes energy from our transmitter and radiates it out into space, and there's bad R. Bad R could be resistive, could be you're using such a small gauge of wire that it's heating up because it can't handle the current. Or it could be a vertical antenna that has, because of this image that we talked about in the Earth, it has ground losses before the radio wave is actually formed fully. We're not going to go into detail on this concept, but just know that with vertical antennas, they have ground losses. Horizontal dipoles don't. They have very few ground losses. So that's a drawback of vertical antennas, is that they'll have more ground loss than a horizontal dipole. So if we have a quarter wavelength vertical antenna, I'm not sure I emphasized, we said that the impedance of a half wave dipole antenna is 73 ohms. A quarter wavelength vertical antenna is half of that. 36 ohms nominally is where the input impedance of a quarter wave vertical antenna is going to be. Still a pretty good match to 50 ohm cable. In fact, if you compared it, it would be 1.39 to 1, which most people would say is perfectly adequate. But if it's a antenna for VHF or UHF, where the radials are something that you don't have to put them on the ground, but you're actually making them to stick out to the side. Here's a trick. If you bend those radials down at about a 45-degree angle, that bending actually changes the center point impedance of a quarter wave vertical antenna and more closely matches 50 ohm coaxial cable, so you'll get a 1-to-1 impedance match. So you can use this for VHF and UHF antennas. You can also use it for vertical antennas for HF if you elevate the feed point. If you put this feed point 15, 20 feet up a tree, for example, and then run your radials, they're called elevated radials, run them down to the ground, you can get a very good match to coaxial cable at HF using this technique. All right, let's talk about loaded antennas. Well, not this kind of loaded antenna, but we talked about the standard dipole antenna. It's going to be 468 divided by the frequency in megahertz will give you the length in feet. So an 80-meter antenna is going to be about 133 feet long. So keep that in mind. The thing is that not everybody has a backyard with 133 feet. Even if you put it in an inverted V configuration, that's a lot of real estate. This is an equivalent circuit of a dipole antenna. It's got capacitance, it's got inductance, and at the resonant frequency, if the antenna is cut properly, these two things will cancel out and you're left with just the radiation resistance. All right? And if we look at another view of a series resonant circuit where X of L equals X sub C, and you go through the math, you come up with this formula, this is angular velocity, but if we characterize it in this way, it's the frequency of resonance of a resonant circuit is equal to 1 over 2 pi square root of LC. So we just rush through developing, but this is the resonant frequency formula. The thing I want to point out in this formula is note that if you increase inductance, it'll give you a lower resonant frequency. If you increase capacitance, it gives you a lower resonant frequency. And we can use this concept by adding lumped reactances into an antenna to make it appear electrically longer. So here's our quarter wave vertical antenna. A quarter wave vertical antenna for 80 meters would be, like 65, 70 feet high. You may not have that room, but if you can add an inductor into the center, for example, and if you can add a capacitive top hat, wires or even a disc or something at the top, by adding L and C, you lower the resonant frequency of this antenna. You make it look like it's longer than it really is. By adding L or C, it's the same as making the antenna longer. Of course, you can't get something for nothing, and you pay with reduced bandwidth. The antenna will not be as broadbanded for standing wave ratio. So, for example, on 20 meters, here's a full low Q half wave dipole antenna, covers pretty much all of the 20-meter band. With a high Q antenna, like you might find on a car or in a very small lot or something like that, the bandwidth is very, very narrow. That's what the difference is between a loaded antenna where you've added inductance and capacitance over here versus an unloaded antenna, which is a wider standing wave ratio bandwidth. I mentioned car antennas, and that's a popular thing to do because you can't get a 60-foot long antenna on your car. So what they'll do is they'll add large inductors and they'll motorize them. They'll motorize the inductor to be variable, so you can short out a certain number of the turns or go down and get more turns. This changes the resonant frequency of the antenna. These are known as screwdriver antennas because Ham started making them. Remember these style electric screwdrivers? Well, they'd take the motors and gearing out of these and put it right here, and that's where they would make screwdriver antennas. These are varying the inductance. Notice that the whip stays the same length on all of these. What's changed here is the amount of inductance that's being added to the whip. So I want to point out this is a loaded antenna with variable inductance, not to be confused with corona balls. Corona balls, you might say, well, is this adding capacitance? No, there's not enough there. This little thing right here, what it does is, if you remember, when we're transmitting, you remember on the half-wave dipole antenna at the far end, it's high voltage, hundreds of volts. Well, the same thing exists for shorter car antennas as well. That you can have hundreds of volts there, and they can discharge arcs out into space. Well, what the corona ball, its purpose is to reduce high voltage discharge from the tip on transmit. It is not a top hat, a capacitance top hat. Okay, we covered some stuff. Let's see how we do. Let's answer some questions. So what is the purpose of a capacitance hat on a mobile antenna?
Charlie.
Yet to electrically lengthen a physically short antenna. You're making a loaded antenna. And what is the purpose of a corona ball on an HF mobile antenna?
Delta.
Yet to reduce the RF voltage discharge from the tip of the antenna while transmitting. And what is one disadvantage of using a shortened mobile antenna as opposed to a full-size antenna?
Charlie.
Yeah, the operating bandwidth is going to be very limited unless you've got one of those motorized things you can move it up and down. So which of the following is a common way to adjust the feed point impedance of an elevated quarter wave ground plane vertical antenna to be approximately 50 ohms?
Bravo.
Do we see that? Bravo. You slope the radials downward at about a 45-degree angle, and that changes the feed point impedance from about 36 ohms to closer to 50 ohms. And which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna?
Delta.
Delta.
Yeah, we see that. It's an omnidirectional antenna. And what is the radiation pattern of a dipole antenna in free space in a plane containing the conductor?
Alpha.
Yes, it is.
Alpha.
It is alpha. It's a figure 8 at right angles to the antenna, or we say broadside to the antenna. And how does antenna height affect the azimuthal radiation pattern of a horizontal dipole at elevation angles higher than about 45 degrees?
Charlie.
Charlie, I think.
Yeah, if the antenna is less than a half wavelength high, then the azimuthal pattern is almost omnidirectional. Low dipole antennas are practically omni. And where should the radial wires of a ground-mounted vertical antenna system be placed?
Charlie.
Yep, on the surface or buried a few inches below ground. And how does the feed point impedance of a horizontal half-wave dipole antenna change as the antenna height is reduced to 1/10 of a wavelength above ground?
Bravo.
Remember that chart I showed you over perfect Earth? That as you brought the antenna down below a half wavelength, it steadily decreases. It keeps going down. And how does the feed point impedance of a half-wave dipole change as the feed point is moved from the center toward the ends?
Alpha.
The feed point impedance steadily increases, yes. And which of the following is an advantage of using a horizontally polarized as compared to vertically polarized HF antenna?
Alpha.
Yeah, think about the possibility of bad R. One of those bad R's are ground losses. So a horizontally polarized antenna has lower ground losses than a vertically polarized antenna. And what is the approximate length for a half-wave dipole antenna cut for 14.25 megahertz? So you know the formula. If you had your calculator, 468 divided by the frequency in megahertz.
33.
33. That is correct. All right, and what is the approximate length for a half-wave dipole antenna cut for 3.55 megahertz?
Charlie?
Charlie is correct. That's the 80-meter band, so it's around 133, 132 feet. And what is the approximate length, read this carefully, for a quarter wave monopole antenna cut for 28.5?
Charlie?
So 468 divided by 28.5 would give you close to 16 feet. But notice the question is asking not a half wave, it's asking for a quarter wave
So it's
monopole.
alpha.
So
That's
it would be
296.
alpha. Yeah, 8 feet. So how does antenna gain in dBi compare to gain stated in dBd for the same antenna?
Alpha.
Alpha.
Not alpha.
B.
B, gain in dBi is 2.15 dB higher. If you express gain in dBi, it's going to be 2.15 dB than higher than dBd would be. Yeah. So which of the following antenna types will be most effective as a near vertical incident skywave antenna for short skip communications on 40 meters during the day?
Alpha.
I'm not sure I mentioned it specifically, yeah, but NIVIS antennas are low antennas, antennas closer to the ground. They're omnidirectional. They're cloud warmers. They send most of their energy up. So yes, a horizontal dipole placed between a tenth and a quarter wavelength above ground would be a good NIVIS antenna. And what is the feed point impedance of an end-fed half-wave antenna?
Delta.
Yeah, it's undeterminate, but it's very high. We know that much. And how does a screwdriver mobile antenna adjust its feed point impedance?
Problem.
Yep,
Brother?
by
How about-
varying the base loading inductance, that variable inductor. And what is the common name of a dipole with a single central support?
Alpha.
Yeah.
That is an inverted V antenna, or upside down V. All right, moving on to Yagi antennas, section 7.2. So typically in a Yagi or beam or directional antenna, the driven element is our old friend, the half-wave dipole. And actually there was a ham in Greenville, actually in Piedmont, that had these up. These were called cage dipole antennas. They had these kind of rings and multiple wires that made this effectively a very large diameter conductor. And this was long. I mean, this was like 33 feet and 33 feet. What the point of all that is that the larger the diameter a conductor, the greater the SWR bandwidth of that antenna. So this antenna was, resonant well all over, the band because of the large diameter of the elements. Well, the same thing is true with the Yagi antennas, and so here's 3-element tri-banders. So here's a high-gain TH3 Junior. I had one of these. It's a 20 meter, 15 meter, 10 meter Yagi antenna, 3 elements, directional. And right now the current price from DX Engineering is $540 for that antenna. Here's a comparable Mosley antenna, the CL33M. That's $1,095. Well, they're both 3-element Yagi tri-banders. The point is that this guy has much larger elements. It's also built a lot more rugged. The spacing actually might be a little different as well. But the fact that these are larger diameter elements means that it's going to have larger bandwidth for the band that it's operating in. And by that we mean the standing wave bandwidth. We looked at this. This is the extreme. This is with a loaded antenna, but the larger diameter elements are going to have greater SWR bandwidth. The narrower, smaller diameter elements are going to have more restricted SWR bandwidth. Vertical antennas, they're great. The DX Commander antennas, I've got one downstairs. I'm going to put it up just as a reference antenna, his classic antenna. But a famous ham axiom is that vertical antennas send and receive equally poorly in all directions. Yagi antennas are great because they've got gain, but there is a problem with Yagi antennas. And the problem is, which way do you go? And the answer to that is an azimuthal projection map. It's a map centered on one location, and it shows bearings to others. So Bruce, if you put me up on the blackboard camera, please. Here is an ARRL azimuthal map. You can actually buy these, I believe, in their store, or if you go to a ham fest. Now this one is centered on the center of the United States, but it gives you a good approximation in directions. And so you might not realize, but if you've got a Yagi antenna and you want to work somebody up in Mongolia, you've got to go straight north. If you want to work somebody in Europe, you've got to go between 30 and 45 degrees. You want to work somebody in Africa? Well, it's actually mostly east, maybe to South Africa, maybe slightly southeast. The Caribbean, of course, is down here. South America is down here. Australia and New Zealand and Papua New Guinea to the west. This helps you know which direction to aim your Yagi antenna. And so you can buy these commercially, or I've got a nice offer for you. At the website of NS6T, and I checked this, it's still good, it worked this afternoon. You can generate an azimuthal map for free. Just go there, sign up, give them your latitude and longitude, and you'll get one printed out, I believe it says a PDF, on your QTH, so you can know in which direction you need to point your antenna. Now, sometimes pointing a directional antenna like a Yagi, you're going for maximum gain, but also sometimes you're going for minimum noise. Certain directional antennas, this is one with a cardioid pattern, which is probably very similar to my hex beam antenna, has a nice null in one direction. And if you've got a noise source that's driving you crazy, then if you point the null toward that noise source, it may be what you don't hear that counts. That can be the beauty of a directional antenna. And the hex beams, for example, have a pretty wide 90-degree front lobe, so you can play with it fairly easily. So here's our standard 3-element Yagi antenna. There's our half wavelength driven element, half wavelength calculated as we have before. You have a reflector element that is about 5% longer than the driven element, and you have a director element that is about 5% shorter than the driven element. So here is a 3-element Yagi antenna, directionality off in this direction. That would be the front of the antenna. This is a 3-element Yagi, and then you can also build longer antennas with longer booms, more directors, for example, and this will give you increased gain and narrower bandwidth. I mentioned my hex beam has about a 90-degree beam width. Well, with more directors, you'd have a narrower beam width. And so these are the things that you can adjust. You can adjust the boom length. You can adjust the number of directors that are in the antenna. You can adjust the spacing, and all of those will give you increased gain and or narrower bandwidth. One of the measurements of a Yagi antenna is the front to back ratio. That's the signal in the main lobe direction over the signal in the reverse direction. that is the front to back ratio of an antenna. And if you want to get into designing your own antennas, this is a great time, because one of the strongest antenna design programs for amateurs for years and years and years has been EasyNet by W7EL, Roy Llewellyn. It was always $100 to $150, but he retired, and so he made it free. So if you go to his website, easynet.com, you can download his last version of EasyNet Pro for free. Now there's a learning curve, but you can design and see what the patterns of the various antennas are, and great fun to play with, and it's accurate. So that if you model it on the computer, it's very likely to perform as modeled, as long as you include the information necessary to get a good model going, like enough samples and good accuracy, etc. If you don't like EasyNet, there's another computer program called Monogal, which was a Japanese-German creation, and you can find here at a German website the ability to download Monogal, which is probably an easier software to use, but still has a learning curve. And remember, I said that with a Yagi antenna, some things to consider are the physical length of the boom, the number of elements on the boom, and the spacing of each element along the boom. All of those are factors that you can plug into the antenna modeling software, and all of those will affect the gain of an antenna. Just want to casually mention that, so we said that the nominal impedance of a half-wave dipole antenna is about 73 ohms. When you add a reflector element and when you add a director element, they're not connected to the feed line. The driven element is. But by placing these in close proximity, it actually reduces the impedance here from 73 ohms down to maybe 20 or even 10 ohms. And so you have to do something about matching in order to get back to a 50 ohm impedance to match your transmission lines. One of the most popular ways to match is something called the gamma match, which has a capacitance and an inductance element with this bar. Note that you're actually connecting the ground of the shield of the coax directly to the center of the driven element. In fact, this can be grounded. And with this capacitor-inductor combination, or here's another pictorial of a gamma match, which has the capacitor as this a metal rod inside an insulator with another metal piece, and here's the inductor link. By using this, you actually can adjust from a 50 ohm impedance down to, say, a 20 ohm impedance. This is one of the most popular types of matching. Notice that the driven element in a gamma match is connected directly to the boom. You don't have to insulate it from the boom. So there's a point of failure on some antennas that you don't have to deal with. Some manufacturers, like the TH3 Junior that we looked at before, as I recall, use insulators on their boom. So here's the boom here, and they use something called a hairpin match, which looks like a short circuit at the feed point. And it is at DC, but at RF it acts as an inductor, an inductive stub. It's what they call stub tuning. So by having this stub here and adjusting its length, you can actually compensate and provide impedance matching for some of the Yagi antennas. So some use gamma matching, some use hairpin matching or stub tuning. And like the TH3 Junior or the Mosley we looked at earlier, they're multi-band antennas. They're using traps here, which are like frequency filters that for the highest frequency, the antenna only uses the center part. Then for the next highest band, it goes out and it uses further. And then for the lowest frequency band, it uses all of the antenna. That's traps. They can look like this. They're inductors and capacitors, and they allow for multi-band operation in Yagi antennas. All right, some questions, and then we'll take a break. So which of the following describes an azimuthal projection map?
Bravo.
Bravo.
Yes, it's a map that shows true bearings and distances from a specific location. And which of the following would increase the bandwidth of a Yagi antenna?
Alpha.
Alpha.
Yeah, larger diameter elements. And what is the approximate length of the driven element of a Yagi antenna?
Bravo.
Bravo.
That's a half wavelength. And how do the lengths of a 3-element Yagi reflector and director compare to that of the driven element?
Alpha.
Alpha.
The reflector is longer by about 5%, and the director is shorter by about 5%. And what is the primary effect of increasing boom length or adding directors to a Yagi antenna?
Alpha.
Yep, you're going to get more gain out of the antenna if you do that. And what does the front to back ratio mean in reference to a Yagi?
Charlie.
You see that, Charlie? The power radiated in the major lobe compared to that in the opposite direction. And what is meant by the main lobe of a directive antenna?
Delta.
Yep, the direction of maximum radiated field strength from the antenna, the front of the antenna. And which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth of a Yagi?
Delta.
Delta.
These are things you can play with in the EasyNEC or the Monogal software. And what is a beta or hairpin match?
Bravo.
No?
No.
Hey. Oh, alpha.
Yes, it's a shorted transmission line stub, or it could be that hairpin wire placed at the feed point of a Yagi antenna to provide impedance matching. Kind of looks like a hairpin. And which of the following is a characteristic of using a gamma match with a Yagi antenna?
Alpha.
Yeah, the gamma does not require the driven element to be insulated from the boom. You guys are doing great. I'm so proud of you. We made it to our intermission time. So let's go ahead and take 5 minutes, if you would, and then we'll come back and finish out our chapter on antennas. Oops, hang on. There we go. We're there. And I'll start up the countdown timer for YouTube. See you back here in 5. So here we are, continuing on with Chapter 7 on antennas. Antennas is a huge subject. We can only begin to skim the surface tonight in a 2-hour class. But what we're doing is emphasizing the test questions that are in the general class question pool related to antennas, hopefully prepare you for that. And then you can put up your own antennas, and that's when the real learning begins. Because remember, you have a license to learn. So we're just getting you started here. That's all we're trying to do. Had some good discussion in the break. Let's carry on and see if we can complete this chapter. We're going to continue with loop antennas, section 7.3. And just be aware that you can put up resonant loop antennas. They're typically a full wavelength long. If it's 4-sided, then each length is a quarter of a wavelength, a quarter of a wavelength, a quarter of a wavelength. This kind of a loop is, for 80 meters, for example, would be 272 feet of wire. For 40 meters, 142 feet. And you could feed it with coaxial cable at a corner and bring it into your ham shack. So this is a resonant full wave loop antenna. You can also have non-resonant loop antennas. Here's one from a ham in North Carolina, Don Keith, 475 feet long. It's omnidirectional. It has many lobes, but it does have a nice low angle of radiation. He feeds his antenna with 450 ohm ladder line. We'll look at that here in just a second. So not even with coax, and uses an antenna tuner to bring that then down to 50 ohms for his radio. Works well on all amateur HF bands. So these are two different versions of loop antennas. Another version of a loop antenna is something that was invented in Quito, Ecuador in 1951. By a ham who was also the chief engineer at HCJB, a Christian radio station in Quito. They had a problem. They were using directional antennas, I'm assuming Yagis, but I don't know, and they kept melting the tips of the elements in the thin air of the high Andes, the high voltage. Remember we talked about the high voltages at the end of the dipoles? Well, it would melt the antennas off due to the coronal discharge, and they had to keep maintaining the antennas. So literally he prayed about it, and he came up with the cubical quad, which is a loop antenna, a full wave loop here as a driven element, and maybe a larger as a reflecting element. The cubical quad is interesting in that it uses the full wave loop. It has a reflector. It's a mechanically awkward antenna, but when you get it up, the 2-element cubical quad has the same gain as a 3-element Yagi. So it does have some advantages there. It has a radiation resistance higher than a Yagi. Remember, the Yagi with the director and reflector parasitic elements went down to about 20 ohms or 10 ohms. Well, cubical quad can be fed directly with coax. It'll work at lower boom heights. A height of 35 feet works just fine. And they're stackable internally. And we'll show you here in a second. So you could actually build larger quad and then inside build a smaller diameter quad and feed with multiple coaxial cables for multiband operation. Very low angle of radiation, and it has a broader SWR bandwidth than a Yagi. So cubical quads have some good properties. This is just for your reference. You can feed the quad at either the sides or at the top or bottom. If you feed it at the side, it's vertically polarized. If you feed the top or bottom, it's horizontally polarized. And here is a spider beam, a spider quad, I should say. And so here's multiple elements, 20 meters, 15 meters, 10 meters on one quad spreader system. And in this case, only one feed line is required. Other kinds of loop antennas, the delta loop. So this is, instead of being a 4-sided like the quad, this is 3-sided, and it can be in different configurations. A 2-element delta loop has the same gain as a 3-element Yagi. The driven element is a full wavelength, so that means that each leg is a third of a wavelength long. And it uses a reflector that is, 5% longer than the driven element. So you see a pattern here? Another, which isn't really a loop antenna, but you see them out there, they're called halo antennas. This is one for 2 meters. This is an omnidirectional, horizontally polarized antenna. This is a halo antenna for 2 meters, horizontally polarized in the plane of the antenna. Another kind of loop antenna that you'll find out there, and I know we're moving right along here, but that's what we do, is a receive loop antenna. I have one sitting out in the backyard here that looks just like this. It's a Wellbrook, and it's designed for receiving over the medium frequency and high frequency bands. It has a FET preamplifier built in right here at the bottom, and it is directional, so it's bidirectional in the plane of the antenna. This is a receive loop. You can't use it to transmit. But there are also very many transmit loops out there as well. And they use, in some cases, a small coupling loop coupled to a big, larger, full-size loop with a tuning system up above, variable capacitance. Current through these is really high, which means that these conductors have to be very massive. And you can build your own out of plumbing. I've done it. I have a 20-meter loop that I built myself. Or you can spend the big bucks. Here is a Ciro Mazzoni baby loop. It's, I think, about 1 meter in diameter. I think that's the baby. $2,000. It's got variable capacitors up here and with an actuator arm here that takes the loop out or in, and it varies the capacitance up here on the top. It works really well. There's some nice videos on YouTube about the Ciro Mazzoni baby loop and how it performs. Very, very narrow bandwidth. It has to be retuned for every frequency that you use it on. But it comes with its own little tuning unit that does it automatically. So for some people with a restricted backyard or HOA, you can just say, hey, this is my sculpture. So it's not an antenna at all. That's the price you'd pay for art anyway. Oh, let's answer some questions. So in which direction is the maximum radiation from a VHF-UHF halo antenna?
Alpha?
Charlie.
It is Charlie. It is omnidirectional in the plane of the halo, which in the one we looked at, it was mounted horizontally, so it would be a horizontally polarized antenna. And so for a weak signal, single sideband, for example, on 2 meters, if you've got a Yagi antenna, it's pointed in a certain direction. But what if DX comes up in another direction? How are you going to hear them unless you know they're there? Well, you have an omnidirectional halo in the horizontal plane, and it can maybe hear it weakly. And then oh, somebody's out there, I got to go find them with my Yagi. So that's the purpose of that sort of an antenna. In which direction or directions does an electrically small loop, less than 1/10 of wavelength in circumference, have nulls in its radiation pattern? Nulls. They're talking about nulls.
Bravo.
Bravo.
Yeah, nulls are broadside to the loop. It's directional in the plane of the loop. All right, some specialized antennas. So if you're going to have an end-fed wire, just note that they're prone to having high voltage RF in the shack. So here's your transmitter, and you connect a wire directly to it, and that's going to be what I'm going to do. Well, the problem is it's going to have high voltage here. It's going to have the other half of the antenna is going to be the ground connection. If you're going to feed it at the end like that, it's going to have high RF currents. I'm using the dipole as an example here. I'm cheating. I'm using a pictorial that isn't right. But just remember that for end-fed wire antennas, you may get a shock on your equipment because there's high RF voltage. Most people don't do this sort of thing anymore anyway. So, stacked Yagis. Oh, you not only have one Yagi antenna, you've got two. And what do we say? How many dB is 2 times gain? 3 dB. So if you put a pair of antennas together, pointing them in the same direction, two identical antennas results in a 3 dB, or half of an S unit, increase versus a single antenna. And you can stack them horizontally or you can stack them vertically. And if you stack them here like we're doing vertically, it reduces the vertical beam width. How can I do this? It reduces that, but gives you further gain going on out. And you can actually drive the antennas with different phases to control the elevation angle, but most people don't do that. They just drive them together. My friend Bob, ND7J, up in Edneyville, put up twin 3-element 6-meter Yagi antennas. Here they are on the ground on the mast getting ready to go up. And this was the antenna tower base. And I was there on the day that we put them up, and away you go. There's two 3-element 6-meter antennas, which gave him a stronger signal than me. I'm jealous. So we talk about adding 2 antennas, getting a 3 dB increase. What do you think if you put 4 antennas up? Yep, another 3 dB, or 6 dB overall, times 4, versus a single antenna. In this case, you get reduced beam width in the vertical, and you get also reduced beam width in the horizontal. We talked earlier about near vertical incident skywave. These are antennas that are close to the ground, so you can use pretty much any dipole. I'm just going to push mute all, see if that works. No, it didn't. They're known also as cloud warmers because they send most of their energy straight up. But any dipole lower than a quarter wavelength has really strong NIVUS properties. And you use these antennas if you're in mountainous terrain, for example, and you want to transmit a signal up to the ionosphere, have it come bouncing back down, maybe on the other side of a mountain, because VHF can't go through the mountain, but NIVUS HF can get on the other side. Just like with the Yagis, where we saw the traps, you can have a trapped multi-band dipole. It allows for multi-band operation with one antenna. So if you have limited space, I can only put up one antenna. Maybe you can have it operate on multi-bands with using traps. Again, with any multi-band antenna, though, it's going to have poor harmonic rejection. On rejections, the harmonics of your fundamental signal will be radiated very well. Another multi-band antenna that my friend Bob, ND7J, had up for a while was a log periodic antenna. He didn't have this one up, but one similar. So a log periodic antenna is one that has continuous operation over a wide range of frequencies. It'll actually operate on 20 meters and 15 meters and 10 meters, and it'll operate on the frequencies in between those bands. In the test question pool, they call this wide bandwidth. Okay. I'm not so happy with that question, but okay. You could say that a log periodic antenna has very wide bandwidth. It can be rotatable or fixed. Here's a rotatable one. If you go to Embassy Row in Washington, D.C., you'll see a bunch of these on embassies in Washington, because embassies use them for direct communications back to their home countries. It does have lower gain than a Yagi antenna of similar size, and it's mechanically much more complex. And the reason they call it a log periodic is because that the element length and the spacing on the antenna vary logarithmically. So you can see here that the length here and the spacing is wide, but here as the length gets shorter, the spacing gets shorter, et cetera, et cetera, et cetera, down to the end. And this is a fixed log periodic antenna that might be used by the military, for example. Another specialty antenna is the beverage named after Harold Beveridge, who worked for AT&T. It's a horizontal wire that is from 1/2 to several wavelengths long. It's used for receiving because it has negative gain versus a dipole antenna. What it does have is noise immunity. So you'll find hams, if they want to work 160 meters or 80 meters, for example, they'll be transmitting on one antenna, maybe a dipole, but they'll have a Beveridge up to listen on. And the Beveridge consists of, feeding with coaxial cable, a 450 ohm 4-to-1, 6-to-1 transformer, a long antenna, multiple wavelengths long, a 450 ohm resistor at the far end, and a ground system. And so this is an easy way to put up a Beveridge antenna. And it's a traveling wave antenna, where signals coming from a far distance come and build up a voltage along the surface of the antenna, where it's transformed and brought back into the receiver. So Beveridge antennas, really great. Only located above, about, they say here, 1.8 meters. 4 feet above the ground is about the optimum. You can go up to 10 feet high if you have to put it up for deer or other things to go underneath it. Or you can even lay them on the ground. It's called a Beveridge on ground or bog antenna, and they work too. I've used them in all of those configurations. A traveling wave antenna, the Beveridge antenna. Okay, here's some more questions. So what is a characteristic of a random wire HF antenna connected directly to the transmitter?
Bravo.
You may get shocked because of the significant RF current that is being carried by the equipment. It's a poor practice. In free space, how does the gain of 2 3-element horizontally polarized Yagi antennas compare to the gain of a single 3-element Yagi?
Bravo.
Yep, 3 dB higher, times 2, remember. And what is the primary function of antenna traps?
Alpha.
Alpha.
Yep, to enable multi-band operation. You'll find them in Yagis and also in dipoles. And what is an advantage of vertically stacking horizontally polarized Yagi antennas? I don't know if
Charlie?
I don't know if I'd call it an advantage. It is delta, because when you put one on top of the other, horizontally, vertically stacking them, I should say, it narrows the main lobe in elevation. And which of the following is an advantage of a log periodic antenna?
Alpha.
Yeah, wide bandwidth. You can transmit on the ham bands and even in the bands in between. So which of the following describes a log periodic antenna?
Alpha.
Yeah, the element length and the spacing vary logarithmically along the boom. And what is the primary use of a Beveridge antenna?
Alpha.
Alpha.
It's a receiving antenna. It's directional receiving for medium frequency and low HF bands. The receiving direction comes in the direction that you put the wire out. So which of the following is a disadvantage of multiband antennas?
Delta.
Delta.
Yep, they have poor harmonic rejection. All right, this is probably the most interesting section in the entire chapter, feed lines. So we're always looking to have a matched impedance. So you have your transmitter or source impedance, let's say 50 ohms. We have a transmission line with a characteristic impedance, let's say 50 ohms. And we have an antenna over here, which we'll say has 50 ohms impedance. If they're all matched, if they're all the same, then all of the energy to be radiated, coming from the transmitter will be radiated by the antenna. And so here's a diagram I found online that I just love. So here is a matched impedance. Consider this to be an energy pulse coming from your transmitter. This is the RF energy. It's coming from the left from the transmitter and going to the antenna on the right. And all of the energy is going out. We're not seeing any of the energy coming back. Energy comes back when it hits a discontinuity. So think about, waves coming from the ocean, coming up against the shore, and they're going to bounce back. There's going to be a rebound wave. When energy, whether it be wave energy or whether it be radio frequency energy, when it hits a discontinuity, then there's going to be a rebound wave. And let's say we have an open circuit. Well, that's going to be 100% of the energy is going to rebound and come back to a transmitter. And this is our energy pulse, and all of it is being rejected. None of it is being radiated because there's no antenna that it's connected to. This is what we're probably going to see with our antenna system, a partial reflection. Some of the energy is going to be radiated off by the antenna, but some of the energy is coming back toward the transmitter. This is a typical scenario. And interesting fact here, from a high impedance to a low impedance, notice that the polarity of the energy reverses. So that you have a positive going pulse and the return is negative going. Or if you go from low impedance to high impedance, like that open circuit, some of it comes back, but the polarity stays the same. So here are the two worst cases: open circuit on the top and a short circuit on the bottom, where all of the energy is coming back. All right, so the reason I mentioned this is because when we're doing our thing with our antennas, we want all of that energy to be radiated. And we measure how well our antenna system is matched to our transmission line using standing wave meters. And bet you've never seen a standing wave before, but I'm going to show you one right now. So if you look here at the blue wave that is going from the left to the right, the blue wave is the energy coming from our transmitter, and the red wave that is coming from the right to the left, that's the energy that is being reflected. And notice where that they algebraically add together, you get this up-down bit of energy on your transmission line. These are actually high voltage points that you can actually measure. In fact, we used to measure the high voltage points on transmission lines in VOA using fluorescent tubes and just walking along the transmission line, and you'd find where the high voltage points were. True story. So that's where these are. That's the high voltage points. This is a standing wave, this black you see right here. And that's what we're trying to minimize, because if you have no reflected power, you'll have no standing waves. And a standing wave ratio of 1:1 is a perfect match. So here's 1.14. That's pretty darn good. That would be most acceptable. So we typically deal with antenna mismatches through the use of, they're either called antenna couplers or antenna tuners. They may be external to your radio, or they may be built in to your transceiver. And what does an antenna coupler or antenna tuner do? It generates, believe it or not, a rebound wave exactly opposite of the reflection coming from the antenna mismatch. So here you've got, let's say, 100 watts coming from your transceiver. It goes into the antenna tuner. You've got power going out to the antenna, and you've got reflected power coming back. And what this antenna coupler does is just send the reflected power back to the antenna over and over and over again. It happens at the speed of light, so it looks continuous. That's all this does, is actually make the transmitter happy, make the transmitter think that there's a 50 ohm load at its output. And the antenna tuner is located, so here's our transceiver. You go into the antenna tuner and then out to the antenna. Well, if that's all the antenna tuner does, and there's also this analogy of using the antenna, it's kind of like the transmission in a car that allows the oddball impedance that's out here to be driven by the 50 ohm impedance of the transmitter. Well, let's say we make all of those adjustments and we get a one-to-one, the transmitter is happy. Well, what happens though with the SWR on the transmission line between the tuner and the antenna? If it was 5-to-1 to start with, it is still 5-to-1. You don't actually change the SWR on the transmission line. Rather, you just send a rebound wave to send the energy back to the antenna. Maybe a new concept, but just think about it for a bit. You can measure standing wave ratio also as impedance ratios. So 50 ohm to 50 ohm is 1-to-1. 50 ohm to 100 ohms would be considered 2-to-1. 50 ohms to 200 ohms would be considered 4-to-1. Going in the other direction, 50 ohms to 25 ohms is also considered 2-to-1. The bigger number is always going to be on the front. So 50 to 25 ohms is 2-to-1. 50 to 10 ohms would be a 5-to-1 standing wave ratio. All right, here's a concept. High standing wave ratio plus line loss. If you have a lossy transmission line, what's it going to give you? It's going to give you hot coax, lost power as heat in the transmission line, because high SWR causes higher total power loss in lossy cable. So I spent some time on this chart, and hopefully it comes through. So if you have a lossy transmission line and high SWR, you're going to lose power in every rebound of energy. Remember I said that energy travels near the speed of light. You're going to lose that energy as heat in the coax. And in this case, with lossy transmission line and high SWR, most of the transmitter power is never radiated from the antenna. So here's a special case. I picked it because it was easy to work with. 100 watt transceiver, transmitter, and tuner. Transmission line, 100 feet with 3 dB loss. And that's how you measure coaxial cable losses per 100 foot. So we've got 100 feet here with a 3 dB loss. And we've got an antenna mismatch of 6-to-1, which I know is 50% reflection. So what happens is you got 100 watts coming here. Half of it is lost on that first go-round, so it's only 50 watts when it arrives here. Half of it is being reflected, and half of it will be radiated by the antenna. So we get 25 watts out on that first go. The reflection comes back at the speed of light. Remember though, half of that is being lost, so only 12.5 watts returns to the tuner. The tuner rebounds it back. Half of that arrives, and you get 3 watts radiated, 3 watts reflected again. It comes back, and it just goes on and on and on infinity. 1.5 watts returns, and so on and so forth. You get, if you add 25 and 3 and the 0.75 here, out of a 100-watt transmitter, you're only radiating 28.75 watts. 71 watts are being lost as heat in the transmission line. So that's why the combination of a lossy transmission line and high SWR is doubly bad. The other thing about lossy transmission lines, if you have a lossy transmission line, it will make the standing wave ratio that you measure in your shack read lower, better than it really is. How's that possible? Well, let's look at our example here. So we send 100 watts out, and we get 12.5 and 1.5 in returns, or only 14 watts back. So we send 100 watts out, we get 14 watts back. That says that the standing wave ratio is 2.2 to 1. It's not. It's 6 to 1. We know that. But the lossy transmission line will make the standing wave ratio look better than it is. And here's a table that, looking at the 14 watts, and that's where I got the 2.2 to 1. So high SWR and line loss will give you high will give you hot coax, lost power, and higher total power loss in lossy cable. So if you're going to have a mismatch, you know it's going to be a mismatch, and it's going to be a long distance that you're going to run. That's why old hams, old timers, have not forgotten about ladder line or open wire line. Here's 450 ohm ladder line. These the ladder line cable has very, very low losses, low dB per 100 feet, like half of a dB per 100 feet. So you can run these things for long distances, even into a mismatch, and still not have the problem that we looked at before. And you may actually get more radiated power. So this is ladder line. Its nominal impedance is 450 ohms. And how is that determined? Well, it's determined by the spacing between the conductors and the diameter of the conductors. And here's the formula if you want to look into it. But those are the characteristic impedance factors of open wire or ladder line. Most of us are going to use coaxial cable. It's the most convenient to use. And 50 ohms and 75 ohms is the total, is the typical characteristic impedance. So here we've got the various flavors of coaxial cable. And as I mentioned, that coaxial cable is rated in dB attenuation per 100 feet. So here's a table of various different kinds of coaxial cable, and you can see that some have very low loss at higher frequencies, others have much higher. But in all of them, as the frequency increases through the coaxial cable, loss will increase, no matter what kind of coaxial cable you're using. All right, let's answer some questions. So what is the purpose of an antenna tuner?
Charlie.
Yeah, it's to increase power transfer from the transmitter to the feed line by making the transmitter happy. So which of the following factors determine the characteristic impedance of a parallel conductor feed line?
Alpha.
I heard you say something, but I didn't hear what it was.
Alpha.
Alpha, yes, exactly. The distance between the centers of the conductors and the radius of the conductors. And what is the relationship between high standing wave ratio and transmission line loss?
B.
B.
Bravo.
Bravo. High SWR increases loss in a lossy transmission line. Yeah. And what is the nominal characteristic impedance of window line transmission line, also known as ladder line?
Delta.
Yep, 450 ohms. So what causes reflected power at an antenna's feed point?
Charlie.
Yep,
Charlie.
the difference between feed line impedance and antenna feed point impedance. And how does the attenuation of coaxial cable change with increasing frequency? As frequency goes up,
Bravo.
always attenuation increases. Yep. And in what units is RF feed line loss usually expressed?
Delta.
Decibels per 100 feet. And what must be done to prevent standing waves on a feed line connected to an antenna?
Delta.
Yeah, you have to change the antenna feed point impedance to match the characteristic impedance of the feed line. And if the SWR on an antenna feed line is 5:1, and the matching network at the transmitter end of the feed line is adjusted to present 1:1 to the transmitter, what is the resulting SWR on the feed line?
Bravo.
Still 5:1. You haven't changed that whatsoever. And what standing wave ratio results from connecting 50 ohm feed line to a 200 ohm resistive load?
Alpha.
Alpha.
See, the ratio of 200 to 5, 200 to 50 is 4:1, so it's 4:1. What standing wave ratio results from connecting a 50 ohm feed line to a 10 ohm resistive load?
Delta.
Delta.
Yeah, remember the big number is always first, so 5:1. What is the effect of transmission line loss on SWR measured at the input to the line?
Alpha.
Higher loss reduces SWR measured at the input to the line. It makes the SWR look better than it really is. And that, ladies and gentlemen, is the end of Chapter 7. We made it. Yay. Congratulations. So proud of you. And are there any questions about anything we've covered tonight?
I've got a question, but you didn't cover it, and that is, what is the point of a remote antenna tuner? I bought one because I didn't know what I was doing, and nobody talks about it. So what did I buy?
Okay, well actually that's a very good thing, because the remote antenna tuner is located at the base of an antenna. Let's say it's a vertical antenna, for sake of what we're talking about. Let's say it's a 66-foot tall wire or tower. You put the antenna tuner there at the base of the antenna, and it works there to match 50 ohms coming in to whatever the antenna's impedance is at that frequency. And therefore, you have a perfect match all the way back to your transmitter. So you have no standing wave ratio, no rebounding energy. It's the best of all worlds. So you've got a good one there with the remote antenna tuner.
Very good. Thank you.
You bet. Anything else? Dave, what are we talking about next week?
All right. Well, next week we're going to be exclusively focused on Chapter 8, which is propagation. We've talked about a lot of good things, antennas, receivers, transmitters, but we haven't really focused too much on how do you get the signal from your location to where in the world you want to talk. And the magic answer is via the ionosphere. So most of the focus of the chapter will be on the ionosphere. And I do have one particular problem that I'll address too. I've got one state where I haven't worked one of the parks yet, on Parks on the Air, and that's Alaska. So what frequency and what time of the day should I be using in order to be lucky in Alaska? So that's a practical question that we're going to answer next week as well. And for you, eventually you'll find a country or a state that you need, and hopefully this information will help you. So read Chapter 8 and be watching for an email from me. I'll provide the Kessler links and a little bit more information. And looking forward to next week.
Thank you, Dave. You get a chance to see Bruce there in the background. He's the guy pushing the buttons. So
Yep.
we'll all say 73, y'all.
Yeah.
Appreciate you being with us. So tune in next week, please. Ciao.
Great job,
Thank you,
guys.
73.
Thank you.
Thank you.